This is an example of a rigid body kinematics problem. Let's read the problem statement. The rectangular plate is confined by rollers within slots A and B. When theta equals 20 degrees, point B is moving at 10 meters per second. Determine the velocity of points C and D at this instant. And the plate dimensions are 100 millimeters by 50 millimeters. All right. So we're going to solve this problem using the concept of the instantaneous center of zero velocity, or the IC. In order to determine the IC, we need to know information about two different points on the body, information about the velocity. In this case, we know that the velocity of VB is going downward. This is what they indicate in the figure. So if VB is going downward, then the velocity of A has to be going to the right, and they're confined to right in these slots, so there's no up and down velocity for A. So we know the direction of two velocities, and with this we can find the IC. So if we draw a line that's perpendicular to both of these velocities, they will meet at the IC. So now we have an idea where the IC is. So let's see how we're going to solve this problem. So the strategy that we're going to use is to avail ourselves of the relative velocity equation, which states that the velocity of one point is equal to the velocity of another point plus omega cross the distance between the 2 points. We're going to just apply this equation several times. But before we apply it, there's one bit of information that we need, and that is the angular velocity. The problem statement doesn't give this to us. So this can be found very easily using the concept of the IC. So we'll find that, and then once we have the angular velocity, we can find distances based on the geometry of the part and find the velocity of any point on that body. So before we go forward, let's look at the geometry. So with this, we're just finding simple distances. So you can see in this figure, I've drawn 3 right-angled triangles. And note that the angle within each of these triangles is theta. All right, using that information and just simple trig functions, we can come up with the distances. So you can see, for example, x1, which is this distance here, is just the side length, which is b, times sine theta. And then y1 would be cosine theta. So just simple trig to get that. And you can do the same for the other 2 triangles. And note that this left triangle that's shown in green is really the same size as the right triangle shown in green. Okay, so we have all the distances, which gives us information on the distance from the IC to point C and to point D. Another nice fact with the IC is that, remember how we located it, the line connecting the IC to the point is always perpendicular to the velocity. So if we take a line and we draw it from the IC to C, then the velocity of C is perpendicular. So we can get a visual of how the velocity is going to look. And the same for D. We draw a line between the IC and D, and the velocity is perpendicular. All right, so we have all the geometric information, and we can apply that and find the angular velocity and then the velocities. So the angular velocity is really easy to find, because if we know where the IC is, it's really like tackling a fixed axis rotation problem. So all we need to know is the velocity of one point and the distance between the 2, and we can find the angular velocity. So V equals r omega, the simple fixed axis rotation equation. Well, we know the distance because we figured that out with the geometry. We know the velocity of, or the speed of, point B, and we can find the angular velocity. All right, now that we know the angular velocity, we can find the velocities of point C and D. If the problem had just stated find the speed of C and D, then we could just use this simple v equals r omega equation again. But they ask for the velocity, so we need directions. So in that case, we're going to use the relative velocity equation and go from the IC to point C and then to point D. So you can see that we have defined omega as being in the k direction, and then we just figure out how far is it from the IC to point C in the x direction and how far in the y direction. We take our cross products and get our result. And we can do the same for point D, using the same equation just between two different points. And the nice thing about having a visual of the velocities, drawing the line and knowing it's perpendicular, is that you can check to see if your equations match up, right? VC, well, there should be some positive value in the x and some positive in the y. That's what the figure shows. D will have a negative in the x and a positive in the y, and that's what we get. So that's a good sign.